So today we will be talking about more MIPS instruction format, the I, J, and R format stuff. So we'll go ahead and get this started. Alright, so computers are built on two key principles. Instructions are represented as data, and this means that entire programs can be stored in memory to be read or written just like data. So everything has a memory address. The instructions that we use, like when you do a LI or an add, the data words, they all have a memory address. And there's this one register that rules over all that called the program counter. It's a pointer to memory. Intel calls it the instruction address pointer. It's like the next thing to be executed on the processor. So we'll look later at jumps and branches, which are similar to like your Boolean ifs and like functions, I guess, if you were thinking in C, and how these modify the program counter to move you along the memory into other parts of the code. So currently we work with 32-bit blocks in words. Each register that we talked about is a word. Load word and store word both access memory one word at a time. So how do we represent instructions? Computers do not understand our literal, like add register T0 or add register 0 and register 0 store in T0. So it stores it in ones and zeros. So this is going to get into the explanation of how that's done. So one word is 32 bits. So what they do is they divide instructions into fields, kind of like the way we divided the floating point number into, you have like the sign and the exponent and the mantissa, is that what the word is? And there's three formats: R type, I format, and J format. I format's probably the easiest. It's used for instructions with immediates. Load word and store word, since the offset counts as an immediate, and the branches, branch equals and branch not equals, but not shift instruction. We'll talk about that later. J format usually used for jump and jump address location, and R format is used for all other instructions. So you define the fields of the following number of bits each. You have 6, 5, 5, 5, 5, 5 for an R format instruction. First 6 bits represents the opcode. The last 6 bits represent the function. Opcode combined with the function basically tells you what it wants to do. Your RS, RT, RD, these are your destination, target, and source. And we'll look here how the target is kind of has a misleading name in certain situations. So the opcode partially specifies what instruction it is. This number is equal to 0 for all R format instructions. Func section combined with the opcode tells exactly what instruction to use for the R format instruction. So you'll see the RS stands for source register, generally used to specify the register containing the first operand. So if you have like add T0, register 1, register 2, register 1 would be the source register. Target register is used to specify the second register. So in that example it would be register 2. And then RD would be, in that example, T0, the destination register. So the name is misleading for target register because target and destination kind of mean the same thing when you think about it, really. So in my opinion, they should have just called it source register 1 and source register 2, but they decided to confuse it a little bit. So don't let that mess you up later on. Each register field is exactly 5 bits, which means you can specify any unsigned integer in the range of 0 to 31, because 2 to the 5 is 30, well, can only represent up to 2 to the 6 minus 1, which would be 31. The word generally was used because there was exceptions that we'll see later. Multiplying, like for example, when we get into other instructions like multiply and divide, they use something special with the high register and low register, and MF high and MF low have nothing important in the RS and RT fields. Well, that's for later on that. The final field is the shift amount field. This tells the amount to shift an instruction by. So shifting in a 32-bit word by more than 31 is useless, so you can represent all the possibilities of shifting the bits with only 5 bits. So shift of 0 doesn't move the bits at all. Shift of 1 moves all the bits to the left 1 and fills in zeros where the preceding bits were, and then we'll lose whatever bit was on the end that moved over. And for a detailed description of field usage, you can see the green insert in the textbook, and that is allowed to be brought into the examination. So looking at this instruction, we have an R format example. Add register 9 with register 10 and store in register 8. Opcode is 0 if you were to go look this up in the book, and the function code is 32, meaning all ones, or 1 with 5 zeros, or 1 with 4 zeros. RS equals 9, the first operand, RT equals 10, the second operand, and RD equals 8. Shift them out, not a shift. So you can actually use this and generate the 32-bit binary to represent add 9, 10, and store in 8. And it would look something like this. So you have the 0 for the opcode, 32 for the function code, 9, 10, and 8. You'll see here this is the RS field, RT field, and RD field. And then there's no shift amount here, so this is set to 0. And you can also go back to the other stuff we did and represent this as hex. So when you see like hex editors, when you're doing like a disassembly, you might see some strange numbers and whatnot. If you know the instruction set architecture and you break the number back into binary, you can actually look it up in a table and figure out exactly what's going on. So more or less, all that this is really doing is sending the number 19,546,144 to the processor, and for some reason it knows that that means add register 9, register 10, and store that in register 8. No matter what, anytime you send that value to the processor, it'll do that. So what about instructions with immediates? These, I think, are the easiest to understand. You have a 5-bit field, represents numbers up to the value 31, so the immediates may be much larger than this. So what they did was they extended that 5-bit field so you can store more numbers. So ideally, MIPS would have one instruction format, but unfortunately you have to make compromises for these other situations. So they defined a new instruction format that is partially consistent with what we spoke about earlier. So the field this time uses a source register, a target register, an opcode, and then 16 bits to represent an immediate number, which essentially means we can only represent numbers from 2 to the 16 minus 1 in a I format instruction. So the only field that's, it says here only one field is inconsistent with R format. Mainly it's missing the shift and there's no RD, so I guess that's more than one thing really. But the opcode is still in the same place. It's basically the last 16 bits are all used for this immediate value, which is straight up just a binary number. That's why it says immediate. It doesn't actually go to an address and look at what's in the address. It's just like add 5, like a literal, just add 5. The number 5 would be an example of using an I format. So the opcode is the same as before, but since there's no function field, the opcode uniquely specifies an instruction in I format. This also answers the question of why R format has 2 6-bit fields to identify the instruction instead of a single 12-bit field, in order to be consistent with the other formats. So you notice how at the one end of the R format and the other end, that's how you actually got what it did. The only reason they did that was so that the other formats would kind of look similar and would be easier to understand and read. So RS specifies the only register operand if there is one, and RT specifies register which will receive the result of the computation. This is why you call it the target address, because for this particular, or target register, for this particular type of instruction, it is the same as a destination. Why they don't call this one RD, I don't know, but RT in this case does act as a destination for an I format instruction. So the immediate field, you have add immediate, set less than immediate, set less than immediate unsigned. The immediate is signed extended to 32 bits, thus is treated as a signed integer. So 16 bits can be used to represent the immediate up to 2 to the 16 different values. This is large enough to handle the offset in a typical load word or store word, plus a vast majority of values that will be used in the set less than immediate instruction. So although you can't get the full like bang for your buck, you don't get like the 2 to the 32. 2 2 to the 16th works in most cases. So the MIPS instruction, add register 22, or add immediate -50 to register 22 and store in 21. The opcode would be 8. RS, the register containing the operand, is 22. RT, the target register, is 21. And then the immediate would be -50. So in that 16-bit immediate field, you would have -50 sign extended represented in 2's complement form. So you can see that here. Here's your 8 for your add immediate. Here's 22 for your source, 21 for the target, which is used like a destination in this instance, not to confuse you, and -50 represented in 2's complement right here. Again, hexadecimal representation, or if you want to think about it, it's like sending the number 584,449,998. So there's quite a bit of combinations you can represent here just by sending a binary number. The whole processor works on that principle. So problem, you have unsigned number sign extended. So you have add immediate unsigned, set less than immediate unsigned to 32 bits. Thus the number is a signed integer. So the rationale is add immediate unsigned can add without overflow, and set less than immediate suffers so that we can have easy hardware. Does this mean we'll get wrong answers? No, it means the assembler has to handle any unsigned immediate number that is greater than or equal to 2 to the 15 and less than 2 to the 16 with a 1 in the 15th bit and 0 in the upper 2 bytes, as it does for numbers that are too large. And that's, I'm not going to go into detail on that, but that's basically talking about overflow protection. The chances are that add immediate, load word, store word, and set less than immediate will use immediate small enough to fit in the immediate field. But what if it's too big? So this is why they have the next instruction format. So you need a way to deal with a 32-bit immediate in an I format instruction due to the fact that you can only represent 16 bits in an immediate instruction. So one of the ways they do it is using the load upper immediate, which all it does is stores in the upper 16 bits of a register. You have 32 bits total. You have the upper 16 and the lower 16. Load upper immediate will store 16 bits all the way in that MSB portion of the number, and then sets the lower half all to zeros. So how can you use this? So say you have a 32-bit number AB, AB, CD, CD, and you want to add it to register T0 and store in register T0. Well, you can load upper immediate the AB, AB into register AT. Then ORing, which when you OR, just to give you an example, it's kind of like when you use logic in with MIPS instructions, it's more like masking. Masking meaning, say I have like 1001 represented here, and I OR it with A, so I OR it with 1010. So this is stored like this if it was only 8 bits. Of course, I'm talking about 32 bits. If I OR it with A, I would OR it with 1010. It winds up just storing, basically like concatenating the MSB portion and the LSB portion. So using this load upper immediate and then the OR immediate, you can get a value immediately. You can extend past the 16-bit limit. And the slides hint that it would be nice if the assembler did this automatically, and something about that later, and I'm not sure what that's talking about off the top of my head. So we'll talk about the J format instructions. These are the ones that modify the program counter. So it has the following syntax: the letter J and then a label, which means set the PC equal to the address of the instruction pointed to by label. So our codes are all these instructions, right? And they're all stored in certain addresses. So if you make a label for it and you say like J function, or test function, or something like that, test function has an address. So when you say J test function, it really just loads some 32-bit number of the location of that in the assembly. So jumps and modify the PC. J and JAL jump to labels, but a label is just a name for an address. So the ML equivalents of J and JAL or the machine language equivalents of jump and jump address location use addresses. Ideally, we could specify a 32-bit memory address to jump to. Unfortunately, we can't fit both a 6-bit opcode and a 32-bit address into a single 32-bit word, so they compromise. And they do a clever trick here. The upper 6 bits represent the opcode, and the whole rest of the thing, the other 26 bits, are the target address. That's fine. But we still need to get to this 32 bits somehow. So we need to compensate for these other 6 bits. So keep the op field identical to R format and I format for consistency, and combine all other fields to make room for a large target address, because if you're dealing with a 32-bit processor, you want to address things 32-bit to get the maximum performance. So the target has 26 bits of the 32-bit address. So the optimization, jump will only jump to word-aligned addresses. So I had hinted at previously that in MIPS, all words, or all data is aligned by words, which is 4 bytes. So due to that fact, that means the last 2 bits of any address will always end in 00. Is that clear why that is? Will always end in 00. Due to the fact that they're aligned by 32 bits. So the next address will always be there's a lot of space. It doesn't increment by 1, it increments by 32. So you have that two bits at the end. So what they do is they take it for granted, kind of like the invisible 1 trick we saw earlier with exponents and floating point. So they just know there's 2 zeros at the end of it. That's cool. So where do you get the other 4 bits? This, what they do is take the 4 highest order bits from the program counter. 99.999% of the time this is correct. This means that we can't jump to anywhere in memory, but it will work for most cases. The limitation being if you straddle a 256 megabyte boundary, which if you're writing assembly code would take you like forever to write anything that made any sense. And if we absolutely need to specify a 32-bit address, we can always put it in a register and use the jump register instruction, which we'll see later on. So the summary is the next PC equals PC 3128, and I guess the next one there would be 25 due to these 4-bit aligns. So the target address, and then you have the 00 at the end. So understand where each part comes from. You get 4 bits from the program counter, 26 bits that are in the register field, and then 2 bits because you always know that it ends in 00. So you can now have 32-bit addressing. And here's 2 ways to do it. The Verilog notation, which uses commas and braces, and then the just straight up 32-bit format. So we have jump and jump address location. What about jump register? So J format won't work, no register field. So use the R format and ignore the other registers. So when you want to use a jump register, all you do is you have the source register, opcode 0, function of 8, everything else is 0. So what about using branch equals and branch not equals? It's a tight fit because you have 2 registers and an immediate address. So the way they do this is opcode, source, target, and then immediate. So what can immediate specify is only 16 bits. But using the word align trick, you can get 18 bits. However, that's still not enough to do 32 bits. So loops are generally, the logic here is that loops are generally small, typically up to 50 instructions. So function calls and unconditional jumps are done using jump instructions, not the branches. So the conclusion, we may want to branch to anywhere in memory, but a branch often changes PC by a small amount. So a jump can change the PC big time, whereas a branch generally, because it's contained in a loop, does not modify the PC counter so much. So solution to branches in 32-bit instruction use PC relative addressing. So you let the 16-bit immediate field be assigned to its complement integer to be added to the program counter if we take the branch. So I know this is a little complicated. You can branch up to 2 to the 15 or minus 2 to the 15 words from wherever the actual program counter is, which should be enough to cover almost any loop. So if we don't take the branch, the PC counter just increments by 1 word. So PC equals PC plus 4. to get to the next instruction. If we do take the branch though, the next value for PC is PC plus 4. Keep that in mind. There's always the PC plus 4 because you have to take into account the actual instruction you're at. So this is next instruction plus the immediate number that you have stored in the immediate field times 4. The reason you multiply times 4 is to align everything by words. So the immediate field specifies the number of words to jump, which is simply the number of instructions to jump. So if that means like it's 19 instructions away, it'd be 19 times 4 will actually get you to the next instruction. So due to the hardware, add immediate to PC plus 4, not to PC. And this will be clearer later. Well, actually be clearer in the very next lecture when we talk about how the memory is stored. So here's some MIPS code. You have a loop here. Branch equals if 9 equals register 9 equals register 0, branch to n. So you can think of it as else. Branch equals any of these branch instructions you think of as if. Like if register 9 equals register 0, go to n. Else, do everything else, which is add register 8 to register 10 and store register 8, and then you have add immediate, subtract 1 from register 9, store back into register 9, and then jump to loop. So go back to the loop. So basically this thing will keep on looping until register 9 equals 0, and you can see that it's decrementing by 1. Is this clear what this code's doing here? All it's doing is decrementing by 1, the value that's in register 9, and adding 10 to register 8 each time it does that. So depending on the value that register 9 starts with, depending on how many times it adds 10. And then n subtracts register 4 from register 3 and stores in register 2. So the branch equals the I format. So the opcode is 4. You can look this up in the table. Storage register is 9, second register is 0. What about the immediate? Well, the immediate, you can see here, it needs to jump through 3 instructions. So I'm going to just go ahead and assume, in this case, and I was correct, immediate equals 3. So you see how there's 3 instructions under the branch equals in? There's add I, j. So what it does is it tells the PC counter, hey, if you branch here, add 3 times 4 to the PC counter plus 4. So specifically, if I get the pointer out here, at the very like if you're running this code, once you hit this particular portion, this is PC. Once this is done, this is PC plus 4. So program counter is going to point to beginning of loop. Program counter plus 4 essentially points to this add-on. So you have, we know the way that this works is it's going to have PC plus 4 times immediate times 4 plus immediate times 4, right, for the immediate field. Reason why you have these 3 instructions. So immediate is going to get the value of 3, and this should make sense here. If everything's aligned by words, so everything's aligned by 4 bytes, you can see that this starts here at PC, then jumps 1, 2, 3, then you add another PC plus 4. Because if you just add 3, you're going to wind up here on J loop, and it's going to keep on looping. You add 1 more, and you wind up at N. So is that clear? So PC counter is constantly telling you where you're at in the program. It is a stack of the actual running memory of your assembly language program. Is this all clear now? Does that make sense? So here's the binary representation of this. So if you were ever to see this code like represented, you would go, well, all right, I can put this back together. This just means I've branch equals to, if 9 equals 0, then I need to move 3 instructions down and go to n. So does the value in the branch field change if we move the code, and what do we do if the destination is greater than 2 to the 15 instructions from the branch? Does the value in branch field change if we move the code? Yeah, absolutely. Well, if you move the code entirely, no. If you start adding things to the code, then yes. And what do we do if the destination is greater than 2 to the 15? 32 bits representing a single instruction. Branches use PC relative addressing. Jumps use PC absolute addressing. So how do we convert? Well, let's go back to this question because that didn't really answer that. What do you do if the destination is greater than 2 to 15 instructions away from the branch? I'm going to go ahead and assume that you can't do that because there's only 15 bits stored in the immediate, and I think they hinted at that earlier in the slides. I'm not 100% sure that that's the answer to that question. If you want to look into that, and let's see here. So here's the different type of the R, I, and the J. Essentially, this is what they look like. So here's, you might be wondering, like, man, this is like so stupid, this machine language. Here's where it's cool. So if you can convert ones and zeros to C code, you can start to disassemble programs or reassemble or assemble a C code into assembly, or you can actually disassemble assembly and find the resulting C code. We don't do that in this course, but that's the magic of what you can do with this. So you look at the opcode. 0 means R format, 2 or 3 means J format, otherwise I format. Then use the instruction type to determine which fields exist, and write out a MIPS assembly code converting each field to the name, register number, name, or decimal hex number. Logically convert this MIPS code into valid C code. Always possible, unique. It's not necessarily always possible to know exactly what's going on because there's certain things that are lost in translation. But for the most part, you actually can look at binary and get the resulting C code. So for example, you have machine language instruction here represented in hexadecimal. So you let the first instruction be at offset 00400000. So convert the hex to binary. Okay, now that it's in binary, you can actually look at it and you know, okay, R formats all begin with 0 for the first 6 bits. So the top 2 here are definitely R formats. I formats are 1, have the value 1 or 4 to 31 stored in them. So I'm going to go ahead and say actually 1, 2, and 3 are R. I looks, the third one looks like an I, and then J is only 2 or 3, so the last one looks like a J, number 6 here. So just looking at these, I would say R, R, I, R, I, J. R, R, I, R, I, J. Let's see if I'm correct about that. So R, R, I, R, I, J. Just by looking at the opcodes here. Then, now that you know the opcode, you know the instruction format, what it looks like. So remember, you can start drawing the boxes in like, okay, well, since this is an I format, I know that these last 16 bits are the immediate portion. So you move here, and this is what it looks like when you actually do that, and you do the decimal conversions here for those examples. And now you can translate or disassemble to MIPS assembly instructions. So once you do that, you look these up in a table, you get the instructions, and you convert them to assembly. Now you can look at it, and this means, okay, or 0 with 0 and store in 2, which basically stores a value of 2 in register, or value of 0 in register 2. Set less than, if 0 is less than the value in register 5, set register 8 equal to 1. Branch if register 8 equals register 0, and move 3 instructions down to that past the J. Then you have add register 4 and register 2 and store in register 2. Then you have add immediate, subtract 1 from 5. I don't know what exactly this does. That didn't make any sense at all, really. Well, I could see the loop here. So you have the loop and the exit. Translate the C code. And this seems to be something that's like product equals 0 while multiplier greater than 0, product plus equals multiple can, or multiplier minus equals 1. So just by looking at all those 1s and 0s, you can take this all the way back up to this. You have to be a little bit creative to figure that out. I don't know how they knew that this had something. What I'm saying about how you lose things in translation is clearly just by looking at a register value, how do you know that it meant product or something like that? But you could have like variable 1 equals 0, and you can look at it, and if you've programmed long enough, you might be able to determine, okay, this function represents this mathematical thing that I saw once in my life. So that should go to show you how the code is all stored in ones and zeros. It's just really interesting stuff. So last thing is just something to think about. When combining two C files into one executable, recall that we can compile them independently and then merge them together. Why? You can compile two C files into one executable and merge them together because they're all binary. So jump instructions don't require any changes, and branch instructions don't require any changes. So you now have all the tools to be able to decompile a stream of ones and zeros into C. So you could start tapping a processor and catching the ones and zeros that are going in and out of there if it used MIPS instruction set only, because we don't know the other ones yet. And you could decompile that into C code if you painstakingly took the time, or you could write a program and do it for you too. You never know. So that concludes the slide for today.